Okay, so today we are going to look at volcanism. Volcanism. So igneous rocks are formed by crystallization from a liquid or magma, and they include two main types. So we have what we call the volcanic or extrusives, and then we have what we call the intrusives or plutonic rocks. And for the volcanics or extrusives, it means that the magma got to the surface. Whereas for the intrusive or plutonic rocks, they form when the magma crystallizes at depth within the earth. So that is the main difference. So volcanic or extrusive, and then intrusive or plutonic. So the two terms are interchangeable. They're interchangeable. And magma itself is a mixture of liquid rock crystals and then gas. And since it's a mixture of liquid rock crystals and gas, it has a lower density compared to the surrounding rock. And because of this density differential, this magma is going to rise upward. So if the magma solidifies on the surface, then we have an extrusive rock or volcanic. And then if it solidifies within, we will have a plutonic rock or an intrusive rock. And depending on the environment of crystallization or cooling, we are going to have different types of textures. So the keyword here is textures. So these are igneous textures. And as far as these textures are concerned, we could talk about three types of igneous textures. Three types of igneous textures. So with these three types of igneous textures, we have first and foremost what we call aphanitic texture. Aphanitic texture. Aphanitic texture. So the term aphanitic means not visible to the eye. Not visible to the eye. Not visible to the eye. And the extreme form of aphanitic texture, we could talk about volcanic glass, or obsidian, volcanic glass. So the aphanitic texture, it means the cooling rate was extremely fast, and so we are not going to have time for any crystals to develop well. So we are going to have this fine grain. The crystals will not be visible to the naked eye. Then we could also have slow cooling at depth. And when we have slow cooling, there is sufficient time for the crystals to develop. So the resulting rock mass is going to have visible crystals, large visible crystals. And we describe that type of texture as phaneritic texture. So we have aphanitic texture, phaneritic texture. So aphanitic means not visible to the eye. And then phaneritic means visible to the eye. Visible to the eye. So granite, for instance, has a phaneritic texture, whereas the basalt or your obsidian will have an aphanitic texture. Aphanitic texture. So either you have aphanitic texture, or you could even have the extreme form obsidian, which is volcanic glass. Volcanic glass. So obsidian is actually just glass. It's only glass because the cooling rate was extremely fast, and there was actually no time for any form of crystal to develop. There is a third type of texture, igneous texture, we call porphyritic texture. Porphyritic. So when you hear the term porphyry, a porphyry, or the texture is porphyritic, think about large crystals surrounded by fine matrix. So how does this kind of texture develop or evolve? For a porphyritic texture, the large crystals develop first. So first we have slow cooling, and then this slow cooling is subsequently followed by rapid cooling. So slow cooling followed by rapid cooling gives rise to this porphyritic texture. Slow cooling followed by rapid cooling would produce a porphyritic texture. So in a porphyritic texture, during the slow cooling phase, we are going to have the development of large crystals. So during the slow cooling phase, we are having these large crystals developing. And then as the cooling conditions change, and then the cooling rate becomes fast, we are now going to have this type of texture. So in this case, we are having this kind of smooth texture. We are having this smooth texture. So in here, we have this kind of texture now, coarse grains surrounded by fine matrix. And that is what we call the porphyritic texture, porphyritic texture. So the large grains here, we call them phenocrysts. And then in between the phenocrysts, we have what we call the matrix or the ground mass. So that is a porphyritic texture. So in a porphyritic texture, we have coarse grains, and these are surrounded by a fine matrix material or ground mass. So that is what we call porphyritic texture. Porphyritic texture. So these are the three igneous textures depending on the rate of cooling. So fast cooling, aphanitic, slow cooling, phaneritic, slow cooling followed by rapid cooling, we are going to have a porphyritic texture. So these are vesicular rocks. So with the vesicular rocks, we have scoria and pumice and basalts. So vesicular rock, vesicle means a hole or voids. So the main difference between vesicular, this pumice and scoria is that scoria has thicker walls and is darker compared to pumice, which has thinner walls. And this is volcanic glass, obsidian, and we have vesicular basalt. So we have a phaneritic texture here, porphyritic texture. Then this is also porphyritic. So in the case of phaneritic, everything must be coarse-grained. We can have a porphyry where the matrix is completely fine, or we can have a porphyry where the matrix is slightly coarse, but with much larger, coarser grains. So these are the two types of textures you could have with the porphyries. One, the matrix is completely fine. In other case, it is not completely fine, but it's still finer than the phenocryst. Then we have the aphanitic or fine textures. There are different types of magma. So when we talk about the chemical composition of magma, it's dependent on the various elements we have in the magma. So we can talk about silicon, aluminum, iron, calcium, magnesium, potassium, sodium, hydrogen, and oxygen. And all this make up about 99.9% of magma. And because oxygen is so abundant, this kind of chemicals typically exist in terms of the oxides. So they typically exist in terms of the oxides. So in that case, we are going to have various oxides, like silicon oxide, aluminum oxide, iron oxide, and all that. So with regards to the types of magma, we have three types depending on the silica content. So now focus. I'm going to use the silica contents SiO2, and we are going to use this SiO2 to discuss different types of magmas and their behaviors. So using the silica contents, I'm going to talk about 5 different things. So please focus. So what are some of these 5 different things we are going to discuss using the silica contents? We are going to discuss the first, whether the magma is what? Basaltic, andesitic, or rhyolitic. In other words, the type of magma. That's the first one with the silica content. Second, we are going to talk about the viscosity of the magma. The viscosity of the magma. That is another one. Next, we are going to talk about the amount of gas content. So the gas content of the magma. Gas contents of the magma. We are also going to use the silica contents in the magma to understand the explosivity of the magma, whether or not the magma will explode, how it will explode, the explosivity of the magma. Also, it can give us a clue about the temperature of the magma. And last but not least, it can also tell us the acidity of the magma. Acidity of the magma. So with the silica content, we are going to discuss these different things using the silica content. The type of magma, the viscosity of the magma, the gas content of the magma, the degree of explosivity of the magma, the temperature of the magma, and then the acidity of the magma. We are going to try to discuss all this using the silica content of the magma. The silica content of the magma. So the first one we are going to talk about now is the type of magma. So we have in here, we can look at 3 different types of magmas, based on the silica content. So we have the basaltic magmas, and they have silica content between 45 to 55%. So we call these the basaltic magmas. Then the andesitic magmas have silica content between 55 to 65%. And the rhyolitic magmas have silica content between 65 and 75%. Now, correspondingly, we expect to have high contents of magnesium and iron in the low silica magmas, high magnesium, iron, and calcium. But then there will be low amounts of potassium and sodium. What about the case of the andesitic? We will have high amounts of iron and magnesium and calcium. So like intermediate amounts for the intermediate magmas. So intermediate amounts of all. And in the case of the high silica content, we are going to have low iron and magnesium and calcium, high potassium and sodium. So the most important thing I'm trying to tell you here is that you should expect high iron and magnesium when we have low silica content. By the way, if the silica content is low in the rock is going to be mafic. So low silica content we would expect that rock to be mafic. In other words, the resulting rock will be dark in complexion. So the higher the silica content, the more lighter the resulting rock will look like. In other words, the more felsic, high in feldspar and silica, the more felsic the rock will be. So this is as far as the three types of magmas and the resulting elements and associated elements are concerned. By the way, basalt, andesite, and rhyolites are all extrusives of volcanics, and their correspondings are intrusives are gabbro, diorite, and granite. So gabbroic, dioritic, and granitic. All right, so what we are saying basically is that we should expect to have a high content of iron and magnesium, as well as calcium, where the silica content is low. So if we have a high content of iron and magnesium and calcium, then we should expect that they should go together with low silica content. So silica content will be low. So the resulting rock will be dark or mafic. But if we have a high silica content, say between 65 to 75, we will also correspondingly have low amounts of iron and magnesium. So the rock will be felsic. So basalt, andesite, and rhyolites, all of them are extrusive rocks, extrusive. But gabbro is intrusive, diorite is intrusive, and granite is what? Intrusive. So, but the magma, the chemical composition of basalt and gabbro are the same. The only difference is that basalt, in the case of basalt, the magma got to the surface and cooled, so fine textured. But gabbro, the magma did not get to the surface and it's cooled. Both rocks will be very dark. Both rocks will be dark. But gabbro will have crystals and basalt will not have visible crystals to the naked eye. Similarly, rhyolites and granite are all felsic, so they'll have low content of iron and magnesium. So both of them, rhyolite will be smooth and granite will be rough because there are crystals, because of the slow cooling rate. So that's basically what we discussed. The next one we are coming to now is the type of magma. So now we know that the type of magma can have an influence even on the color of the magma, because if there is low amount of iron and magnesium, the rock will be dark. If there are high amounts of iron and magnesium, the resulting rock will be light colored. Let's go to the next one, viscosity of the magma. Viscosity of the magma. We understand viscosity is like the thickness of the magma, right? The viscosity of the magma. Viscosity of the magma. For the magma to be viscous, it's dependent on the silica content as well. Magmas that have a high silica content will be more viscous. In other words, they will be more resistant to flow. But basic magmas, when we say basic, it means silica content is low. And when we say acidic, it means silica content is high. So when we talk about magmas, basic and acid, they are like geologic descriptive terms. So when we say a magma is basic, it means that magma does not have a lot of silica in it. Low silica content magmas are called basic magmas, basic. And if the silica content is high, like the felsics, we call them what? Acidic magmas. So we have acidic magmas and basic magmas, just like your acids and bases. But in geology, these are more descriptive terms when we talk about the magmas. So the higher the silica content, the higher the viscosity, the more explosive the magma will be, the higher the gas content, basically. So the temperature would also be low in this case, because this rhyolitic or granitic magmas would have a lower temperature, roughly between 600 to 650 degrees Celsius. But every other thing will be high. Every other thing will be high. So we'll now continue and look at exactly how all this come into play as far as the various types of magmas and then the behavior of the magma with respect to the silica content is concerned. So at depth in the earth, nearly all magmas contain gases. And this gas gives magmas their explosive character because the gas expands as pressure is reduced. What are these gases? So these gases are mostly water with some carbon dioxide. These gases are mostly water with some carbon dioxide. And they have some minor amounts of sulfur, chlorine, and fluorine gases. So when we talk about rhyolitic or granitic magmas, they usually have higher gas contents than basaltic or gabbroic magmas. So you realize that the higher the silica contents, the higher the gas contents of the magma. The higher the silica contents, the higher the gas contents of the magma. That is what this basically means. The higher the silica contents, the higher the gas contents of the magma. The higher the gas contents of the magma. So we see how the silica content is able to tell us or give us a lot of information about the kind of magma we are dealing with. Then, when we talk about basaltic magmas, these are magmas that form at very high temperatures, 1000 to 1200 degrees Celsius. Then andesitic, 800 to 1000 degrees Celsius, and then rhyolitic, 650 to 800 degrees Celsius. And with the viscosity, once again, I told you that viscosity is a resistance to flow, and higher silica content magmas will have higher viscosity than lower silica content magmas. So it means that at low temperature, the low temperature magmas will have higher viscosity. And I think this is quite the case even in everyday life, where at lower temperatures, we tend to have higher viscosity than at higher temperatures. So lower temperature magmas like the rhyolitic or granitic magmas would have a higher viscosity, meaning they are thicker and they'll be more resistant to flow. They'll be more resistant to flow. So we have used the silica content to describe first and foremost the color of the magma or the color of the resulting rock from the magma. We have used the silica content to describe the gas contents of the magma. So we learned that the higher the silica contents, the higher the gas contents of the magma, right? We have also used the silica content to describe whether the resulting rock will be dark in complexion, dark in color, or light in color, or felsic. So we are saying that in a magma we have gases. There are gases in the magma, and these gases in the magma are mostly water with some carbon dioxide. And then we have some minor amounts of sulfur, chlorine, and fluorine. But then rhyolitic magmas have more gases than the basaltic magmas, meaning the higher the silica content, the higher the gas content. So that's what we said. So let's continue now. So magmas have gases, and these gases are mostly water with some carbon dioxide. When we talk about basic magmas and acidic magmas, we mean magmas with low silica content and magmas with high silica content. A magma that has low silica content is described as basic. And a magma that has high silica content is described as acidic. Acidic. So this acids and bases concept is more descriptive than your regular chemistry acid and bases that you know of. Okay. The higher the silica content, the resulting rock would appear, the higher the tendency of that rock to appear light colored or felsic. The higher the silica content, the higher the gas contents of the magma. The higher the silica contents, the higher the viscosity of the magma. The higher the silica contents, the higher the ability of the magma to explode. So the higher the explosivity of the magma. The higher the silica contents, the higher the explosivity of the magma. The higher the explosivity of the magma. The only thing that is going to be low, that corresponds to low or high silica contents, is what? There is one feature that corresponds to high silica content. Any ideas what that is? So the higher the silica content, it gives us a clue that that's the temperature of that magma should have been relatively low at about 600 to 650 degrees Celsius. Yeah, so that's as far as that is concerned. But then when we look at the rest, every other thing appears, how do you call it? So you can talk about 650 to 800. Up to this entire range is still considered relatively low. It's still considered relatively low, all the way up to about 800. Although 650, 600, 650 is kind of the average or the standard. But up to 800, we can still consider this as rheolitic. So we see that everything is, as far as the temperature is concerned, relatively low, but with high silica contents, we have low amounts of iron and magnesium and calcium, high amounts of potassium and sodium. The resulting rock is basically, the resulting rock is going to be light colored. The resulting rock is going to be light colored. Light colored. And then with the basaltic, we should expect basalt, so it's dark colored. So the resulting rock is dark colored. And the reason the rock is dark colored is because the magma had a low silica content, 45 to 55. So it's going to be mafic, whereas this is going to be what? Felsic. So this is called a basic magma, and this is an acidic magma. Acidic magma. So with regards to the explosivity, the non-explosive eruptions are favored by low gas content and low viscosity magmas. So these are the basaltic to andesitic magmas. So it means that the magmas that are more explosive are the magmas that have a lot of gas contents, and they are also viscous. And this corresponds to the silica content magmas, the high silica content magmas. That's the rhyolitic or granitic type of magmas. So we could also have these basic magmas forming what we call pillow lavas. And pillow lava is when we have an eruption into water, and then we are going to have this kind of shape like a pillow kind of in the water. So this is a pillow lava. This is a pillow lava. Pillow lava, like your word pillow, pillow lava. So when magmas reach the surface of the earth, they erupt from a vent. They may erupt explosively or non-explosively. And the ones that do not explode or react non-explosively, these are the basic magmas, because the silica content is low and the gas content is low. But those that explode are the rhyolitic magmas, because they have high silica content and they have high gas content. And the reason they explode is because the gas is literally trapped. The gas is trapped. So when the gas is finally released, we are going to have this kind of extreme kind of explosivity. So explosive eruptions are favored by high gas content and high viscosity. And the expansion of the gas bubbles is resisted by the high viscosity. And so pressure will build up. And this high pressure in the gas bubbles will cause the bubbles to burst when reaching the low pressure at the Earth's surface. So the gas bubbles will burst when they reach the Earth's surface, and then that is what will cause the explosion. So the bursting of these bubbles fragments the magma into pyroclast and tephra, or ash. Pyroclast and tephra. And these clouds can rise way above the volcano to produce an eruption column that can rise up to 45 kilometers into the atmosphere. So this is about the power, the explosive potential of magmas. So the magmas with high silica contents are more explosive. They are more explosive. When we use the term pyroclast, it means hot, broken fragments. Pyroclast means hot, broken fragments. And these loose assemblages of pyroclast are called tephra. So pyroclast results from the explosive ripping apart of magma. Like, think about an explosion. So it explodes and releases hot, broken fragments. That we call pyroclast. And when we put together these pieces and particles of pyroclast, we use the term tephra. Tephra. And depending on the size, tephra can be classified as a bomb, or as a lapilli, or as an ash. So the bigger ones are the bombs, followed by lapilli, and the fine ones, small particles, are ashes. The rock that we form by accumulation and cementation of tephra is a pyroclastic rock. Pyroclastic. So clast means particles, and pyro. So pyro comes from magmatic vents, hot, broken. So pyroclastic rock, pyroclastic rock. So when we have some degree of welding or cementation of the particles, we form a pyroclastic rock. So these are actually, they look like sedimentary rocks, but they are volcanic rocks. Think about the rocks I kind of displayed much earlier, where we had a dike running across. So that is, and then I was standing in front of a dike, and then we had some kind of whitish rocks to the left and right. So these were volcanic tuffs. So these are volcanosedimentary rocks. So these rocks are formed from the pyroclasts that have been cemented together. So they are volcanosedimentary rocks. So the popular name for this kind of cementation of tephra is a pyroclastic rock. Pyroclastic rock. So tephra that falls from the eruption column produces what we call a tephra fault deposit. And pyroclastic flows are typically associated with this type of mafic magmas. They will travel at a far higher speed. So when we have a pyroclastic flow, it means that the magma is flowing. And this kind of pyroclastic flows, they can be very rapid, and the speed, they travel at very high speeds, and they are the most dangerous type of volcanic eruption. So they can travel at very high speed, especially the basic magmas with low viscosity, and they're the most dangerous. You cannot outrun this kind of flow, so you just say your last prayers. And the deposits that are produced from this type of flows, we call them ignimbrite. So this kind of deposits produced from this type of flows, the deposits are called ignimbrite. We also have what we call lateral blast and debris avalanches. So these lateral blast and debris avalanches They have to do with there's a sudden collapse of a flank of the volcano, and then we have the entire mass running at very high speeds. So lateral blasts, these are horizontally directed clouds of gases and extremely hot particles. So we call this ones lateral blast. We call this ones lateral blast. And then we also have what we call debris avalanches. Debris avalanches. Debris avalanches. So this is as far as the lateral blast and debris avalanches are concerned. So an avalanche, you can think about, for instance, when we see an avalanche, it means that we have a collapse of something like a geomaterial. Think about it in terms of, say, even snow. We can have this ice collapses, and then it's going to travel at a very high speed. So we call that an avalanche. So debris avalanche or large landslide kind of avalanche. Or a volcano, when we have these debris avalanches, it means there's a collapse of the column, and this could be very dangerous. It's because it's going to slide downslope. It's going to slide downslope. So we call that a debris avalanche. So as far as the pollutants are concerned, we can talk about the dikes which cut across pre-existing rocks. So these are intrusions that cut across pre-existing structures. And the geologic term for that is discordance. Discordant. So a dike is a shallow intrusion that shows a discordant relationship. Discordant means cutting across to the rocks in which they intrude. Then we have what you call the sills. So the sills, think about them as parallel kind of intrusions. So the geologic term for that is concordance. Concordance. So sills are shallow intrusions that show a concordance relationship with the rocks that they intrude. They show a concordance relationship with the rocks that they intrude. So the new terms we are learning now are discordant and concordant. You've already met dikes and sills, but now we are introducing new geologic terms: discordant, meaning cutting across, and concordant, meaning parallel to the existing structures, the pre-existing structures. So we have the discordance and the concordant. We also have laccolith, batholiths, and stocks depending on the size of the intrusions. So the biggest intrusions are the batholith, and then we have the laccolith, and then what? The stocks. So that is also for your information. We also have batholith, laccolith, and then what? Stocks. Now, how does magma intrude? How does magma intrude a pre-existing rock? There are three ways. One is by melting, meaning it melts everything, so there will be crystallization. The second is stopping. So stopping means that it is fragmenting or breaking the rocks, so we could end up having xenolith. And the last one is by injection. To have injection, we need fissures. What is a fissure? A fissure is a tiny crack. So we need this kind of tiny fractures or fissures. Fissure. So a fissure is a tiny crack. Fissures. So we have these tiny cracks, and the magma will rise through them along these tiny fractures. So here we have a xenolith. So this is by stopping, or the general crystallization. We could have melting or crystallization. So that is how magma intrudes pre-existing rocks, either by melting, by stopping, or by injection. The origin of magma. Magma forms under special circumstances. So under these special circumstances, think about, for instance, where we have a subduction zone, and then we are going to have melting of crustal materials. So magma forms under special circumstances because the earth must get hot enough to melt the rocks present. So under normal conditions, geothermal gradients is not going to be high enough to melt the rocks, but under special circumstances, we have magma forming. And for pure minerals, there are two ways in which we could have this type of melting. So as pressure increases in the earth, the melting temperature will also change. And for pure minerals, there are two general cases, which we call primary melts and parental melts. So that is just for your information. That is just for your information. That brings us to the concept of Bowen's reaction. And in Bowen's reaction, we are able to determine the order of crystallization, like fractional crystallization. So think about traveling from, say, Accra to Takwa. So you get to Takrady and somebody has reached his or her destination. The person alights from the vehicle. You get to Agonankwanta, another person alights. And then you get, finally, you get to Takwa, another person alights, and you get to the station, and the last people alight. So that is the concept of the Bowen's reaction. And Bowen found by experiment that the order in which minerals crystallize from a basaltic magma depends on temperature. So in this, what we call the crystal fractionation, at very high temperatures, the first elements to form or to crystallize out of the melt will be olivine. So after olivine, so the first to come or crystallize, form crystals, olivine. So olivine forms at very high temperatures. After that, we'll have pyroxene forming, and then we are going to have amphibole. So, and then we are going to, as this continues, we are going to have biotite. If you recall from when we treated the topic weathering and erosion, we mentioned that the elements that form, or the minerals that form at relatively high temperatures are more susceptible to weathering compared to the minerals that formed at relatively low temperatures, say the 650 to 800 degrees Celsius kind of temperatures. Now, there is something interesting about this order of crystallization. So when the temperature was still hot, we had these minerals crystallizing out. And as the temperature is reducing, so from 1,200 to about 600, more crystals are crystallizing out. So the magma originally can be basic. If we say the magma is originally basic, it means that this magma had a low silica content. But as we continue to remove this iron and magnesium and from the melt, and we are forming this kind of minerals like your olivine, your pyroxene, and your amphibole. With time, the resulting magma will now have a lot of silica left in it because all the iron and magnesium have been removed and the calcium. So we have more silica left. So you can start with magma that was originally basic or basaltic, and you can end up as a rhyolitic magma. So you see, at this point, a lot of minerals are formed. So the resulting liquid is now rich in silica. And then finally, we are going to have some kind of felsic rock forming, like your granite or your rhyolite, depending on whether the magma reached the surface or not. So here we have this Bowen's reaction. So olivine, pyroxene, and amphibole. Hornblende is a type of amphibole. Then biotite. And then we also have, at the same time, calcium-rich plagioclase, so sodium-rich plagioclase. So our focus is on the fact that some minerals will form first at high temperatures and the rest of the minerals will form at low temperatures. The minerals that form at low temperatures, like 600 or to about 800, are more stable or more resistant to chemical weathering compared to the minerals that's formed at high temperatures. So that is the concept of the Bowen's reaction series. As far as the types of volcanic rocks are concerned, we can talk about obsidian, pumice, vesicular rock, And then we can talk about the amygdaloidal basalts, the amygdaloidal basalts. When we say an amygdale, it simply means that we have a rock with holes. And when these holes are filled, the fillings are termed amygdales, the fillings. So we have a rock with holes. So the rock with holes is what? It's a vesicular basalt, for instance. You see, here we have vesicular basalt. So if I fill this with, if we should fill this holes, for instance, these holes are filled. So if I should fill all these holes with a secondary mineral naturally, then these are amygdales. So we now call this rock that had a lot of holes that have been filled. We call it an amygdaloid. So an amygdaloidal basalt. So that's the meaning of this amygdaloidal. Amygdaloidal means the holes that were existing have now been filled. So we call that an amygdaloidal basalt. Amygdaloidal basalt. So we have obsidian, which we already know. We have pumice. We have vesicular rocks, rocks with holes, and we have the amygdaloidal structures, or amygdaloidal basalt. We also have a crater, which is a depression caused by explosive ejection of magma or gas. So we call that a crater. We can have shield volcano, usually basaltic in nature. So it forms a type of a shield. Then we can have this pyroclastic cylinders. We can have pyroclastic cones or cinder cones, pyroclastic cones or cinder cones. So here a volcano built mainly of tephra fault deposits, so pyroclastic cone. Yes, so with the amygdaloidal basalts, for instance, we tend to have this kind of calcite or quartz filling this kind of voids. So it's very common to find the infillings are typically quartz or some kind of calcite. Calcite is like your calcium carbonate. So these are the type of specific materials that tend to fill this kind of holes. So the pyroclastic cone or cinder cone, we also have that. And it's a volcano built mainly of tephra fault deposits located immediately around the vents. So we have this. Then there's the shield volcano. Then we also have a stratovolcano. So strato tells you we are dealing with strata or layers. So stratovolcano. And we have what we call a lava dome, which is a steep-sided volcanic structure resulting from the eruption of high viscosity, low gas content magmas. So this is a steep-sided structure resulting from the eruption of a high viscosity, low gas content magma. So that's a lava dome. So we see a lava dome and then various types of structures as far as volcanoes are concerned. We can also talk about a crater versus a caldera. When we talk about a caldera here, it means that the entire vents or depression has collapsed into the volcano cavity. And then the crater is just the top, the parts where with the vents, where the magma erupted from. When everything collapses inwards, we are going to have what we call a caldera. And these have become very beautiful sceneries because everything collapsed here. So it forms huge holes or depressions or craters, kind of, or in this case, calderas. And when over millions of years, we had water filling them, so they become natural lakes and tourist attraction sites. So we have these beautiful calderas that have become tourist attraction sites, very beautiful sites. We could also talk about thermal springs and geysers. So hot water resulting from heating by magma at depth, and fissure eruptions. So eruptions along narrow cracks or fissures. So you remember we talked about eruption or the type of intrusion of magma, and we mentioned stopping. We mentioned melting, and we also mentioned injection by fissure eruptions. And we also talked about the pillow lavas. That is eruption in water, given the surface around it kind of appearance, called pillow lavas. So this brings us to the end of volcanism. This brings us to the end of volcanism.